Well, this is the module number 8, density histograms and normal curves. This information in the book, or the topics about this section in the book, they are covered in the chapter number 11. All right, let's start with the density histogram. First, we have 500 YouTube students were asked to give their height. The data is presented and summarized in the next table. So we have here the information for the height given in inches. And we have other column that is the number of students. The sum for all these numbers should be equal to 500. Well, I mean, it is equal to 500. So what do we have here? Here we have values between 60 and 62 inches. But remember, this is not exactly a closed or an open interval. The bracket means, remember, that we do include the number, and the parenthesis means we do not include the number. So here we are saying all the real numbers between 60 and 62. But we do include the 60, but we don't include the 62. So all the numbers between 60 and less than 62, all the numbers between 62 and less than 64, and so on. So how many values we had between 60 and 62? 25. Between 60 and 64, less than 64, 90. Between 64 and 66, less than 66, 210, and so on. Now, once we have the table, we're going to create another table. Another column. This column is going to be the relative frequency. How do we create the relative frequency? It's simple. You have to divide every value for every row by the total number of values. In this case, it is 100. So here we're going to divide 25 over 500, and so on. $25 over 500, 90 over 500, 210 over 500, 135 over 500, and 40 over 500. This is 0.05. 0.18, 0.42, 0.27, and 0.08. These are the values for the density. For the relative frequency, I'm sorry. Now, we are going to create the column for the density. You include another column that is called density. How are we going to compute this? the density is going to be computed relative frequency divided by the length of the interval. So for example, the first one is going to, by the way, notice that for each interval that we have here, the length is going to be 2. How do you compute that? Only subtract the right extreme minus the left extreme. 62 minus 6 is 2, 64 minus 62 is 2, and so on. So the length for every interval is going to be the same here, but that's only a coincidence. It doesn't have to be the same necessarily. Anyway, if it is not the same, you will have to be careful about that and use this formula. So divide 0.05 by 2. So we have 0.025, 0.18 by 2 divided by 2, 0.09, 0.42 divided by 2, 0.21, 0.27 divided by 2, 0.135, 0.08 divided by 2, 0.04. There you have. These are the values for the density. So relative frequency is computed by every value by the total number of values, and the density, every relative frequency divided by the length of the interval, of each interval. Again, the length for each interval here was the same, but maybe for some examples they are not going to be the same. So what is this for? Now we have this. We can create the density histogram. How do we create that? In the next way. Density histogram. All right, so you're going to create one vertical axis and one horizontal axis. Now here, in the horizontal axis, you're going to put the labels with the numbers for the extremes of the interval, 60, 62, 64, 66, and so on. So for example here, 60, 62, 64, 66, 68, and 70. There you have. And here, in the vertical axis, you are going to put the labels for the numbers relative to the density. The division it's up to you how to make the division. But here, since the minimum value for the density is 0.04, I'm going to do it 0.05, 0.10, from 0.05 to 0.05. There you have. So we have here, this is the height. Height in inches, and for the vertical axis we have the density. So now next we have to create rectangles. So it's going to be a histogram. Is kind of the same histogram that we have done before in a previous section, but here instead of using the relative frequency we have to use the value for the density. So we're going to match the intervals with the density. For example, from 60 up to 62 is 0.025. So identify the height. 0.025 is approximately the midpoint between the 0 and 0.5, so it's going to be here. I mean, if you're doing this by hand, of course, you can do it approximately, no problem. So it's going to be here. There you have. You're going to create rectangles. The height is going to be determined by the value of the density. From 62 up to 64, 0.09. It's approximately here. .64, 66.21. 0.21 is approximately here. .66 to 68.135. 0.125 is approximately here. And 68 to 70.04. And there you have, this is the density histogram. All right, what is this for? With the density histogram, you can compute the relative frequency. I mean, the main point of this is that with the area in the density histogram, it's the same as the relative frequency. Or proportion. Or percentage. Or probability. The area in the density histogram is the same as the relative frequency, proportion, percentage, or probability. So for example, if you want to know what is the proportion in this case of values, or in this case students, with a height between 60 and 62, only compute the area for this rectangle. Example, find the area the proportion of students with a height between 60 and 64 inches. So how do we do that? It's simple. Identify here 60 and 64 is going to be the area for these rectangles. It's going to be this region here. So how do we compute this area? Area is equal to the width of the rectangle 2 times the height determined by the density is 0.025. So it's going to be 2 times 0.025 plus 2, this width now, times the height, that is 0.09. And this is going to be 2 times 0.025 plus 0.09. Point 23 or 23%. You see? So what is the proportion of students with a height between 60 and 64 inches? 23%. One property, and you can do this for any other region, right? I mean, the purpose of this is that computing probabilities, proportions, or percentages is equivalent to compute the area for the rectangles. That is the key for this. With graphically computing areas with the density histogram, it's the same as computing proportions, probabilities, or percentages. Of course, one important property of any density histogram, the total area of the density histogram is 1. If you guessed that, you were right, is 1. If you sum all the areas for the density histogram, for any density histogram created in this way, all with the sum is going to be 1. Now, I wanted to pay attention to something else. Notice what happens if I try to join. Let me use another color. What happens if I consider the midpoint in the top for every rectangle? Here, 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 and here. The midpoint for the top of every rectangle. Now, join with the smooth curve those points starting from here. You see that? What do we have here? We have something like this. So we can say with this is the shape of the density histogram. Of course, in this case, I'm not saying that this is going to be always the case. This is going to depend, obviously, on the data that we have. But we can identify, or we can have an idea about the distribution or the shape for the data based on the density histogram. This is called a density curve. So, when the shape of the density curve for a given data based on a sample from a population is bell-shaped, we say that the distribution of the data is normal, or that it has normal density. So when the shape of the density curve of a given data based on a sample from a population is bell-shaped, it might suggest, so we're going to accept that the shape for the distribution for all the data, for all the population, is going to be normal, or it has normal density or a normal distribution. So the key to identify when we're talking about a normal distribution is that it has this form. The density is bell-shaped, like a bell. See that? For this kind of density it can be modeled, or it can be explained with a mathematical function. I'm not going to include it here, but I will explain how to compute probabilities for this when we know that some data is normal. Many population of numerical values or of values in the real life, they behave in this way, like a normal distribution. But why? Because the key of this is that, for example, go back to the example of the heights. How can we interpret this here? I mean, if the area is the proportion or the percentage, yeah, this means that most of the area is concentrated around the center of the distribution. You see that? First, always when we know that the data is bell-shaped or it has a normal density, in the middle always we have something called the mean. Well, we know what the mean is, but it is denoted by this notation. This is the Greek letter capital mu, mean. So when we have the normal density, we know that we can assume that most of the values, or most of the percentages, they are around the mean. For example, here, again, go back to the example of the height, we can expect that most of the students, they have a height very close or around the average or around the mean. That in this case will be approximately like a 65 inches. And persons with a very high height, they're going to be only a small proportion, or it's going to be only a small area. What happens with person with a very low height? We can expect that it's the same. They're going to be only a small proportion. So many things in the real life, they can be modeled with a normal curve or a normal density. I mean, they have a normal distribution. Height, one of them. What about the weight? Is one of them. For example, scores for some exams, they can be modeled in this way. Why? Because again, most of the values are around the mean. Very extreme values are very uncommon. A small proportion, and very high values or very low values, they are considered extreme. They have a small proportion. Most of the values are going to be concentrated around the mean. All right. So always when we have a normal density, we need two parameters to work with a normal distribution we need to know the mean and the standard deviation. By the way, this symbol is the Greek letter mu, and this symbol is the Greek letter lowercase sigma. Mu, sigma. Mu, sigma. But the point here is that they represent the mean of the standard normal distribution and the standard deviation. So we're going to need these two parameters to start working with a normal distribution. Now, one example from Achieve. Properties of a normal distribution. It says, select the statement that describes a normal distribution. First, the normal distribution is a continuous distribution. That is true. What else? The density curve is symmetric and bell-shaped. I just explained this. Of course, it is true. What is the meaning for symmetric? Symmetric means that if you draw a vertical line exactly passing through the mean, for example, this, a vertical line exactly passing through the mean, yeah, then the normal curve is divided into two parts, this one and this one. Well, this vertical line works like a mirror for this part and this part. In other words, this part is a reflection of this part. That's why we say, that's the meaning when we say that it is symmetric. So yeah, it is true. The density curve, I'm sorry, I showed the wrong one. The density curve is symmetric and bell-shaped. This portion is a reflection of this portion, so this is true. Now, what other ones? Two parameters define a normal distribution: the median and the range. That is not wrong. That is not true. The density curve is stratus cube. That is wrong. Approximately 5% of values fall more than 2 standard deviations from the mean. This is going to be true. I'm going to explain this later, but by now you can select that this is true. And then the next one, the normal distribution is a discrete distribution. This is wrong. So these are the three options that you have to select for your question on a chip. Now, another example. The distribution of a bladder volume in men is approximately normal with, notice, we're going to be given the mean and the standard deviation. Mean 550, standard deviation 100. In women, we have two data sets, for men and for women. Women is mean 400, standard deviation 75. Refer to the plot of these two distributions and use 68, 95, 99.7 rule to answer the question. So what is this rule about? Let me explain this rule. This rule is known as the empirical rule. And it said that first, approximately 68% of the values fall on the interval mu minus sigma, comma, mu plus sigma. Another one, approximately 95% of the values fall on the interval mu minus 2 times sigma, comma, mu plus 2 times sigma. Remember, sigma is the standard deviation and mu the mean. And approximately 99.7% of the values fall on the interval mu minus 3 sigma, comma, mu plus 3 sigma. 68% for mu minus sigma or mu minus 1 sigma, mu plus 1 sigma. 95% mu minus 2 sigma, mu plus 2 sigma. 99.7% mu minus 3 sigma, mu plus 3 sigma. So we have to use this rule here. I'm going to do it for the previous example. By the way, this rule is known as the empirical rule for normal distributions. I mean, this is true. All these properties are true once you know your data follows a normal distribution. So here we know that it's normal, so we can apply these rules. For example, part A, it says, between what volumes do the middle 95% of men's bladders fall? So 95%, we have to use this condition, mu minus 2 to compute this interval, mu minus 2 sigma, mu plus 2 sigma. 95%, we have the interval mu minus 2 times sigma, mu plus 2 times sigma. And this is equal to, what is the value for mu? Mu is 550 and sigma 100. Let me write it here. For men, mu is 550, sigma is 100 for men. So let's do it. 550 minus 2 times 100, comma, 550 plus 2 times 100. You see, like that. And this becomes 550 minus 200, comma, 550 plus 200. And this becomes 350, comma, 750. So there you have, we have the interval, but it's asking only for what? It's asking only for do the middle 95% metal blonde. The lower value is this one, 350. So right here, 350. Now in the same exercise, upper value is this one, 70-50. 70-50. There you have. Now, what percent of men's bladders have a volume larger than 650? All right, in this case, we will have to use by now, we cannot use this, the empirical rule, but we can use the normal, we can use Minitab to compute probabilities about this. How to use Minitab? I'm going to explain how to do it. Go to Minitab, yeah, and then notice, I'm going to show you how, oh, something happened. All right, I think now it's working. All right, so go to Minitab, go to Graph, choose the option Probability Distribution Plot, View Probability, OK, and then choose the option Normal, and type the mean. Notice in our example, we're talking for what percent of men. So we need the information for men. For men, we have 550 and 100. 550 and 100. This here. You will need to enter this into Minitab. 550, 100. There you have. Now options. Go to options. And since we're looking for the probability, you have to write specified x value. You need to provide the specified x value because the question is what percentage. So we're looking for the area. Minitab is going to do everything for you. Now choose in this case, since it's greater or larger, because it says larger here, you see that? Larger, then use the right tail, larger. Then x value equal to 650. See that? And then OK. And notice, Minitab is going to create the density curve for you. You see that? Here we have the mean, 550. The value that for which we're looking for the percentage, 650. And this here is the area, 0.1587. But it says we have to round it up to whole numbers, so it's going to be 16. There you have. Now, between what values do almost all 99.7% of women's bladder volumes fall? Now we have to do it for the women. Women They have mu equal to 400 and standard deviation equal to 75. And we need to use the empirical rule here, but now for women. This is going to be the part A, and I'm going to do here the part C. That okay? I did the part B here. This is the part C. And this one was the part A. Yeah, I hope there's no confusion. So I'm going to do the part C here. The part C, I have to compute apply the empirical rule for 99.7%. Apply the empirical rule for 99.7%. So 99.7%, compute mu minus 3 sigma, comma, mu plus 3 sigma. This is equal to 400 minus 3 times 75, comma, 400 plus 3 times 75. This becomes 400 minus 225, comma, 400 plus 225. Then subtract is 175, comma, 625. So how can we interpret this? We can say that most of the values for the distribution for women, they fall between 175 and 625. You see that? Most of the values. Not most of the values. 90, to be more precise, 99.7% of the values, they fall inside this interval. So what is the answer here then? Lower value 175 and upper value 625. You see? There you have. All right. Now let's continue. Oh, we have another exercise in the same problem. How small are the smallest 22.5% of all the bladders among women? Well, in this case, I think we have to compute the empirical rule for 95%, but for women, because if you do a sketch of the distribution for women, it's normal. The mean is 400, so this goes in the middle, the 400, and 95% means that we have 400 plus 2 standard deviation, and the area, the shaded area, is going to be 95%. 2 plus sigma, 2 minus, mu minus 2 sigma, mu plus 2 sigma. So what is the region here? If the area under the curve for any normal density, I said it was 1, so this area here, total area under the curve is 1, so the area in red has to be 5%. But since we have symmetry, this area should be the same as this one. So here we have 2.5%. 2.5%, I'm sorry. And here we have the same, 2.5%. So we're looking for that. We're looking for this one here. So apply the empirical rule. The empirical rule for 95% is this one. Mu minus 2 sigma, mu plus 2 sigma. So it's going to be mu minus 2 sigma, mu plus 2 sigma. So it's going to be 400 minus 2 times 75, comma, 400 plus 2 times 75. So it's going to be 400 minus 150, comma, 400 plus 150. And it becomes 250, comma, 550. There you have. But the question is only smaller than, so it has to be 250. Because this value goes here. This is equal to 250. And this is equal to 550. So the answer is 250 in this case. 250. There you have. Now, the distribution. This example continues here. The same as before. Distribution of bladder volumes in men is approximately normal with mean 550. The same information. The same information as in the previous exercise. But now we have new questions. It says use the technology of your choice. Well, in this case, I'm going to use Minitab. How large are the largest 10% of bladders volumes among women? So first, I'm going to sketch here a normal curve representing the bladder for men. We know the mean here is 550. Notice, if we're looking what is the largest 10%, that means that we're looking for a number such that the area after the number is 10%. That okay? How can we compute that? Well, we can use Minitab. But I did the sketch for the area so you can identify easy what we're looking for. But now we have to go to Minitab. Again, I recommend to do it in probability distribution plot. View probability, okay. Type the mean and the standard deviation. If you see, they are the same that we already have here. 550, 100. Options. How do we know what is the one we have to choose here? Well, look at the sketch that I did. It's this one. So we have to choose this portion, right tail. And now, notice. Now we have the proportion or the percentage. We need to specify that. We're looking for the number. So use the specify probability and type 0.10. Be careful. Do not write it in percentage. Write it in decimals. 10% is 0.10 in decimals. Okay. And the value is 678.2. Well, it should be correct, but 678.2 If this doesn't work, try with the answer from a chip. The answer from a chip is 678.16. I don't know, maybe a chip use a different software. This is the answer we obtained from Minitab. And this is from a chip. So they are slightly different. If you have problems, so use the one from a chip. But you notice they are very close. Now, how large are the largest 5% of bladder volumes among women? Part B. So part A, part B. Again, I'm going to do sketch. This is for men. Now for women. For women, the mean is 400. And now we're looking for how large are the largest 5%. So this has to be to the right because it says the largest. So we're looking for a number such that the area here after the number is 5% because it said the largest. So again, go to Minitab. Minitab, go to graph, probability distribution plot, view probability, okay. Be careful that you enter the right, now the mean for the women. The mean for the women is 400. Standard deviation is 75. Options, now change 5%. 5% in decimals is 0.05. And use again the right tail. Okay, okay. And there you have. This is the answer. 523.4. This one here. You see? 523.4. Again, 523.4. Or if this doesn't work, the answer from Minitab is 523.36. Yeah? I'm sorry, 523. So there you have. Yeah, I know it's a problem. I'll round it up, but yeah, I'm working with Minitab. Minitab says it doesn't. By now, I haven't found how to make possible that Minitab provides only more decimals, but no problem. You're seeing how I'm doing this. You are seeing how I am doing this, and I think that is the most important point. The answer from a chip is slightly different, but I think that's okay. All right. It says obtain and compare the first quartile of bladder values for the population of adult men and for the population of adult women. The first quartile for men and for women. Quartile, remember, is what? The quartile, Q1, it has 25% to the right and 75% I mean 25% to the left, 75% to the right. So you can look for this in two ways in Minitab by providing the 25% and the 75%. Notice, for example, I'm going to do it with the 25%. 25%, go to Minitab, graph, probability distribution plot, view probability, okay. For women, well, we need the two quartiles, quartile one for both. So I'm going to do it. Notice we already have here the information for women, so let's use it. But here in options, write 0.25, but 0.25 in the quartile, the first quartile is 0.25 to the left. So use left tail, and then OK. And there you have, is 3490.4. Q1 for women. $349.4. There you have 349.4. Now Q1 for men. So do the same. Graph probability distribution plot, view probability, OK. The mean here was for men was 500. No, 550. 550. And the distribution is the standard deviation is 100. I'm sorry. And here leave it in the same way. 0.25 to the left. OK. And now notice you have the quartile is 482.6. And if you already have this, notice you can find the solution only by noting the answers. For men is 483 rounded up, and for women is 349. So it's going to be this and this. So this is the answer. There you have. All right. Example, growth chart. The distribution of heights of both 5-year-old boys and 7-year-old boys is approximately normal. Yeah, what I mentioned before, many data sets or variables in the real life, they follow a normal distribution. The mean height of a 5-year-old boy is 43 inches, and the standard deviation is 1.43 and 1.8 inches. The mean height of a 7-year-old boy is 48 inches, and the standard deviation is 2.1 inches. John's height was 44 inches on his 5th birthday, and to date on his 7th birthday he measures 49 inches tall. What can you conclude about the rate of John's growth when compared to other boys his age? All right, here we have to compute something that is called the standard score. Let me explain this. First, standard normal curve. Or distribution. Let me write it better, distribution. Standard normal distribution. It is a normal distribution but with mean or mu equal to 0 and sigma equal to 1. It is represented usually by the symbol C, like that. So, turn any normal distribution into a standard distribution. How do we do this? It's simple. Use the next formula. C is equal to x minus mu over sigma. This is called the standard value. So here we have to compute that. The C for a given score of 5 and the C for the h of 7. So at x equal to, what is the first one? The first one is 4, 5. So first, x equal to 5. X is equal to 5. What is C? We're going to need mu and sigma. Mu and sigma are what? No, I'm sorry. I did it wrong. Let me fix this. First, at the h of 5. The value of x is the height in inches. It's this one, 44, on his fifth birthday. You see that? So x equal to 44. I'm sorry for that. So x equal to 44 inches. The mean is for 5-year-old boys is 43 and the standard deviation is 1.8. 43 and the standard deviation is 1.8. So then C is equal to x minus mean divided by the standard deviation, what is the same? 44 minus 43 divided by 1.8. And I got 0.55. How many decimal we have to use? 3 decimal places. 3 decimal places, then it's going to be 0.556. This is the first C we need. The first C. Now, add the h of 7. At the age of 7, x is equal to what? This is the age of 5. The age of 7 is here. But on his 7th birthday, he measures 49 inches. This is the one. So this is 49. 49 inches. The mean is different and the standard deviation as well. So the mean for 7-year-old is 48 and the standard deviation 2.1. 48, 2.1. So C is x minus mu divided by sigma, or what is the same? 49 minus 48 divided by 2.1. 49 minus 48 divided by 2.1. And I got C equal to 0.476. That okay? So 0.55, 555, and 0.476 for h of 7, for the h of 5 and h of 7 respectively. So write down this here. 0.555 and 0.476. There you have. Now, the option here is, notice how the standard score decreased a little after the age of 7. So we choose John has been growing slightly slower than average because his C-score has decreased a little bit. It's this one. John has been growing slightly slower than average because his C-score has decreased a little bit. It goes from 0.555 to 0.476. All right. Other example, ant traffic. Researchers recorded the speed of ants on trails in their natural environments. The ants studied Leptogenes processionalis all have the same body size in their adult phase, which made it easy to measure speeds in units of body length per second. The researchers found that when traffic is light and not congested, and speeds vary roughly normally. Again, normal distribution with mean equal to 6.2 and standard deviations 1.58. What is the probability that an ant's speed in light traffic is faster than 5 lengths per second? All right, so notice here for the part A, again, I'm going to do a sketch. We know this follows a normal distribution. So it must have this shape if we draw the density. The mean is exactly the value that is in the middle. That is 6.20 in this case, 6.20. Now, we're looking, the question in this part, in the part A is faster than 5. So notice that 5 is to the left of 6.20 because it's less. So it must be at some point here. So only do a sketch. I'm going to do it here. 5. That okay? So what is the probability that an ant's speed in light traffic is faster than 5? So we're looking for all of this area. Area we are looking for. How do we do that? We have to do, I'm going to do it in Minitab. So go to Minitab, graph, probability distribution plot, view probability, okay. Change the mean and the standard deviation. In this case, the mean is 6.20 and the standard deviation is 1.58. Options. Be careful about what we're looking for. That's why I made this sketch. 6.20 the mean, the 5 to the left, but we're looking faster, so it has to be greater than 5. That's why I'm putting this area. That is the area we're looking for. The shaded area after 5. This one. So go to Minitab, choose the right tail. We have the x value. We're looking for the probability. So choose a specified x value is going to be provided. And choose the one 5. Then OK. OK, and then you're going to have the chart. You see that? 5. Notice how it is to the left of 6.2. And the area is 0.7762. Point 7762. .7762. But you know, I don't know. The answer from a chip is 0.7764. I tried to verify that my answers, and I verified them with another application, and it said that my answer is correct. I think a chip got this answer because they used the table. We don't need to use the table here. I mean, if you have Minitab, use Minitab. So if this answer doesn't work, use this one from a chip. Minitab, a chip. Now, part B. What percent of end speeds in light traffic are slower than 6 lengths per second? So we have to do the same, but now notice it says slower. So for this, I'm going to do the sketch again. Draw a normal curve. In the middle, we have the mean, that is 6.20. Now locate the number 6. Number 6 is to the left of 6, so it's going to be more or less here, 6. But now notice it says slower, so it means behind 6. So the area we're looking for now is behind the number 6. All the area behind. Area we look for. And now again, go to Minitab. Graph probability distribution plot. View probability. OK, the same mean, the standard deviation. Options. Now change the value of phi by the value of 6. But now be careful. We're looking for the area behind, so use left tail. Left tail. OK, OK. And you're going to have, notice, this graph with the area we're looking for. The area is 0.4496. So it's going to be 0.4496. Again, maybe, but I have to express this in percentage. It's going to be 44.96%. There you have. But in Minitab, the answer, on a chip, the answer is 44.83. Again, I think it's slightly different because they have used the table. And when you use the table, the approximation is not very precise. It's more precise if you use Minitab. But well, I think a chip, in this case, they use the table. So in case it doesn't work, this is the right answer you should enter. Answer from a chip. Yeah, they are slightly different. The similar percentage is already here. There you have. Finally, what are the 10 and 90th percentiles? 10 percentile means this. Again, draw a normal curve. The mean 6.2 is in the middle. What is the 10th percentile? Is the value such that the probability to the left or behind under the curve is 10%. It's going to be a value here. Area equal to 10% or 0.10. And what is going to be the 90th percentile? The same but with the area 90% behind. So all of this area. Area equal to 90% or 0.90. So we're looking for what values here and here makes this and this possible. So again, go to Minitab. Graph, probability distribution plot, view probability, okay. The mean and standard deviation are okay. Options. First, well, in both we're going to use left tail, but here we need to provide the probability. So it's going to be first 0.10, then okay. And there you have. The 10th percentile is 4.175. But again, the answer we got here is slightly different from a chief. Try on a chief. If this doesn't work, try this answer, 4.1776. A chip. Yeah, again, I think that they're slightly different because Minitab doesn't provide many decimals or because they're using the table. Anyway, this is the right answer. But notice, they are almost the same. And for the 90th percentile, the same, go to graph, probability distribution, view probability, okay, options, the same, left tail, but now change the probability to 0.90 because we're looking for the 90th percentile. 0.90, okay, okay. And there you have the area behind that makes a 90% of the area. The number is 8.225. 8.225. So this is the answer. 8.225. And the answer from Achieve, yeah, is this, 8.2224. So if this doesn't work, if this one doesn't work, use this one. All right, that's all by now. See you in the next video.